Great. Yeah, so as Jeremy said, I'm going to be talking a little bit about finite model theory. And so what that is it's a branch of classical logic, which is concerned with studying how expressive certain logics are for looking at properties of finite structures. Model theory by itself it's a pretty big subject, but a lot of the results are less useful when we want to limit ourselves to only looking at finite things, which is often what we care about in computer science. So I'll go a bit more into the details later, but I'll first sort of just go through a quick recap of how classical logic is set up in case anyone hasn't seen it, but I'm guessing it'll be familiar with most people. So yeah, logic is mainly concerned with two things. There's syntax and semantics. And syntax is just how we build sentences. There's sort of a, sorry, yeah, had my notes in the wrong place. Yeah, so we can come up with things that look like for all x plus 2 is greater than 0, whatever. And we'll just think of this as like a string of symbols that's part of the syntax of the language. And so syntax is usually defined relative to certain symbols that kind of generate the syntax. So we'll have like constant symbols, which in the previous example might be something like a 2 or a 0. We can have function symbols, which as before, there's like a plus, which is it's a binary symbol because it takes 2 inputs, and there's also a minus, which here is a unary symbol. And there's also relation symbols, which as before, there's the greater than symbol there, and that's a binary symbol as well. And then if we want to actually talk about what these things mean, that's when semantics comes in. So the semantics is basically a set which we kind of tells us what the values of the logic is talking about are, and then as well as ways in which we can interpret the symbols that we've defined down here. So in this example, the semantics for this might be a set of naturals that that's wrong. Set of naturals that look like that, and so on. But maybe also it could be open interval in the reals, or similar thing, but restricted to the rationals. And so we call these things models, and they're models of something, and that is this thing here. So they're models of S. And this thing that I've sort of specified over here, this is called the signature of the logic. And that's usually written as a sigma or other lowercase Greek letter. So more formally, the signature is given by a sequence of constant symbols, a sequence of relation symbols, and potentially a sequence of function symbols, but I've kind of written this grayed out because it's often we'll just want to ignore this, especially because you don't really need them in your logic. You can just encode them in relations and have something like f of x, y equals z encoded as some relation where that includes x, y, z. And if you want to actually talk about the value, then you can just use like a quantifier to bring a variable in scope and do that. So the last thing we need in the signature is the arides, which just say how many inputs the relation or function symbols are taking. So in the previous example, we had like the less than relation, and that had aride 2. And down here, I've also kind of made up a relation RF, and in that case, that would have aride 3. And so then from that, we can we can talk about the syntax that's generated by that signature. And this consists of two things, which are terms, and terms represent the values that the logic is actually talking about. So that's, when I say values, I mean like quantities rather than truth values. So that'll be things like sort of, it can be a variable or something built up from a variable and other function symbols, or a constant symbol. And here's the grammar for that. It's pretty simple. And the next thing is formulae. And they're the things that represent the actual truth values. And so they can be things like sort of propositions like this, in which x is appearing as a free variable, or it can be quantified over x. Here we have for all x. And the grammar for that is a little bigger, but it's, again, pretty straightforward. You can have like and symbols, or symbols, negation. You've got existential, quantification, universal, and sort of perhaps most interestingly, you can use relation symbols, and you then need to specify a number of terms where the number is the arity of that relation symbol. And also we've kind of like added in an extra relation for equality that's just always there in the signature. Well, it's not in the signature, it's omitted from the signature, but it's always there in whatever logic we're looking at, because it's quite a fundamental notion, and the semantics of that are fixed as being what equality should be. So next we look at what semantics are, and semantics are always are given by some structure, which I've written as kind of a sort of strange curly A here. And it's also defined relative to a signature, which is sigma here. And so this is like a concrete specification of the collection of objects that the logic is talking about. So that's what this set here is. It's usually called the universe. And then the next thing we need to do is give an interpretation for the various symbols in the logic. And so that gets written usually with these double brackets. And relation symbols are interpreted as subsets of, or sets of tuples of elements of the universe. And here I've got this is just the arity of the relation symbol. So as before, when we had the less than thing, that would be interpreted as some subset of a squared. Yeah, and then the next thing is constant symbols, which are just interpreted as elements of A. That's a bit more straightforward. So yeah, I can give a bit of an example. If we have a signature here which has sort of two symbols, this one I'm thinking of as a binary relation, and this one just a constant, then we might have, say, A, B, just let's say the natural numbers, and then the interpretation of the less than symbol. Well, so at this point there's like no restriction on what it should mean. It could be any set, it could be the set of 0, 0, and that's it. But if we wanted to give like a more natural interpretation, it might be something like 0, 1, 0, 2, so on, 1, 2, 1, 3, etc. And that's again a subset of m squared. And the final thing then is there's a constant symbol, so we just have to interpret that as an element of the naturals. So you can interpret that as 0. And that's all the data you need to specify a structure of a signature like this. And so then these semantics kind of extend to interpretations of the other bits of syntax in the logic. So that is to terms and formulae. So terms are interpreted as functions, and the K here is, this is the number of free variables in the term T. So if T was something like X plus Y minus Z, then the interpretation of this is going to be a function from A cubed to A. But if instead these weren't free variables and were instead just numbers like 2, 1, 0, then this becomes 0, and we'll actually usually just think of this as an element of the set A. The next thing is interpretation of formulae, which we again just interpreted as subset or sets of tuples of A. And again, this is the number of free variables. So for example, this might be X is greater than 4. And then the interpretation of this would just be a subset of A, which is all the elements which are indeed greater than 4. In the case where K is 0, then this is going to be a subset of A0, which is either a one element set or the empty set. So we can think of this as just being a set of truth values, or it takes one of two possible, it can be one of two possible things, which is equivalently a truth value. And so in that case, it makes sense to talk about whether a sentence is true in a given structure. And yeah, so if there are no free variables, we call it a sentence rather than a formula. And then we can talk about its truth, just because it's slightly nicer notation to write this than to talk about whether there's a sort of empty tuple in the one element set. And so from there, we can go on to talk about what actually is a model. And models are sort of considered relative to theories, which is just a set of sentences over some fixed signature. So we then say that a structure is a model of a theory if every sentence in the theory is true in that structure. And so I can give a bit of an example here for groups. So signature for groups might be, it'll have a constant, which is just going to be the identity element of the group. So I'll call that A. It'll have one unary function symbol, and that will send an element to its inverse, so I'll write it like that. And then there's a binary function symbol. Right, that's a function rather than a relation. And that will just be the group operation. And so then we have some axioms, which are the sentences that exist in the theory. And so we need to say what the identity element is, for example. So that'll look like for all x operate on the identity equals x. And there's the other way around, where the identity operate on x equals x. We need to give some meaning to the inverse. So we can say for all x operating inverse equals identity. And then the final thing is associativity. So this is a complete specification of the theory of groups, and what so then a model of this is exactly a group. Like every group is a model and every model is a group. And that is kind of like, it's a lot of definitions to say what a model is, but it's quite a straightforward concept. It's just something that satisfies all of these axioms. And so that's all great, but sometimes we might want to define a theory for something, which it turns out actually we can't do with first order logic. But it's kind of tricky to prove that. And one common tool in sort of classical model theory is the compactness theorem, which says that a theory has a model if and only if every finite subset of it also has a model. And so if you have some like crazy infinite theory and you want to decide whether or not whether there's a model for this, what this allows you to do is consider some finite subset of it, and it can be kind of more easy to reason about whether or not those axioms are consistent. But also it lets you prove quite a common use is to prove an inexpressibility result by contradiction. So I can show an example of this for connectivity of graphs. So the signature for a graph is very simple. It's just one relation, which is the edge relation. And so the way this works is, as I said, by contradiction. We assume that there is some magical sentence that expresses whether a graph is connected. And in case anyone doesn't know, a connected graph is one where just for every pair of vertices, there's some path of edges that goes between them. That's what it sounds like. And then what we want to do is define some formula which says there's a path of fixed length between two vertices. And that's actually pretty easy to do. You just need to put in a lot of existential quantifiers, n of them, and then check that there's for each element each element is being quantified over, there's an edge from it to the previous one or the next one. And so looks something like this. But then what we'll do is we can take the negation of this, and what this does is if you put this in a theory, it forces your graph to be like, I guess, larger than a certain size, but it always does have a model, because if you have some graph that looks like this with your y here, then you can make it into a model for this sentence by just adding a lot of extra edges like that, calling that one y prime, and as long as this is like n vertices long, this has a model. But if we take the union of this axiom over all n, then suddenly that can't have a model anymore, because it's saying there's well, it can't have a model anymore if we consider it in conjunction with this sentence that defines connectivity, because it's saying that there's no path of finite length between two vertices. And so the other slight subtlety here is that I've come up with these symbols C1 and C2, because there needs to be some fixed pair of vertices that every axiom can talk about. So actually now I'm talking about a theory over a different signature with two extra constant symbols. But again, all of the previous stuff can be done over that signature. And if this works over sigma, then it will also work over sigma with these two extra symbols adjoined. So yeah, we have this, and I think it's pretty easy to convince yourself that this can't have any model, because it's saying it must describe a connected graph which has two distinct vertices with no finite path between them. But if you take any finite subset of it, then this will only hold up to some n. And as I showed before with the little picture, you can just keep that will always have a model. And so that contradicts the compactness theorem, and so shows that connectivity isn't definable. And that's great, but this is talking about models in general, and what we're interested in here is finite models. So you might say, okay, maybe there's no magical sentence that does it for all possible structures, but maybe there's one that works only for finite models. And so it'd be great if we could use the compactness theorem, but restricted specifically to the case where we only want finite models here and here. But unfortunately, that doesn't work. Specifically, this is false. And it's pretty easy to see that. You just define a formula like this, which is essentially saying that there are at least n elements in the universe, because it's got a chain of n existential quantifiers, and then it just says, like, has a whole load of not equal between, like, pairwise each of the elements. And any finite subset of these sentences should, well, it will have a model. It's just a set with n elements. But if you take the union of that, well, it does have a model, but it doesn't have a finite model. And so that kind of suggests that compactness isn't really useful for working with finite structures. So we need some other sort of tool for working over finite structures. And one way to do this is with Ehrenfeucht-Freisee games. I apologize for my pronunciation of that. I've never managed to work out how to put my mouth in the right shapes to say it. I'll just say EF games going forward. So what an EF game is it's given by 3 bits of data. There's some fixed signature sigma, and then there's 2 structures over that, and it depends on a natural number k. And it consists of 2 players. There's a player known as the spoiler and players known as the duplicator. And the idea is the spoiler wants to show that these 2 structures are different, and the duplicator wants to show they're the same. So as I said, it takes place over k rounds, and in each round, it starts with the spoiler just picking an element of one of the structures, and the duplicator has to follow that up by picking an element from the other structure. And after k rounds are played, we end up with these like tuples of elements from each structure, like A1 through AK, and you can kind of imagine these tuples generating a substructure of the corresponding A and B. And so then what we say is if after k rounds the substructures generated by A and B are isomorphic, and an isomorphism when we're dealing with structures is just a bijection which respects the interpretations of the relations in the constant symbols. Yeah, if A is isomorphic to B, then we say that this duplicator has won, and that this A and this B are indistinguishable in the k-round EF game. And there's that put a little more formally, and we can kind of write it as like this. And so what this is kind of capturing is the idea of there being like a partial isomorphism between the structures that the players exhibit. And how we actually use this to discuss the expressivity of logics is using something just called the EF theorem, which says that a property is inexpressible if and only if for every k we can come up with two structures for which the duplicator always has a winning strategy, but one of the structures, say A, has property P, but the other structure B doesn't have property P. And so I can give a bit of an example of this too. So if we wanted to go back to the connectivity example and show that like actually it isn't possible even if we only care about finite structures, then what we need to show is that for all k there are two graphs, one which is connected and one which is disconnected, but so that the duplicator still has a winning strategy in the game played over those two graphs. And I realize I've kind of left out a crucial word here, but this should say over finite structures. So the difference here is that EF games do actually give us the power to talk specifically about finite things. So the idea here is you just have to, based on the value of k, make these cycles big enough so that there can never be enough vertices chosen which that you can show that there's like two distinct cycles. So wherever the duplicator goes, you might say pick a vertex here, and then the spoiler picks a vertex here, and then the duplicator just has to pick one vertex in the other structure here to send that vertex. So maybe he'll say there, at this point it doesn't matter, and the spoiler might say here, and the duplicator then has to send it, well, either to here or to here. It doesn't matter at this stage. And the idea is that the spoiler has to keep playing to try and show that these two things are different structures. But as long as these cycles are big enough, they locally look the same, and the spoiler will never be able to demonstrate that. The actual details of proving that is kind of a little finicky. There's a lot of kind of sort of combinatorial arguments you need to make to show that no matter which way the spoiler plays, they'll never actually be able to choose the right elements. So yeah, this is cool, but it's kind of tricky to come up with a convincing argument as to why there's a winning strategy one way or the other. But the crucial thing here seems to be that the property we're looking at it's a global property of graphs. They can, and in small regions of the graph, they can look completely the same but disagree on that property. And so we can kind of formalize this as like a locality property of first order logic. And the way we do this is, well, we first need a way to say what does it mean for two things in a structure to be nearby. It makes sense for graphs, but for other structures, it's a less precise notion. So we'd find this thing called the Geifman graph, which is a graph just whose elements are elements of the universe of that structure. And there's an edge between two elements if they're related by some element of a relation. So in the case of graphs, we just recover the original graph through this construction. But in the case of, say, if we have a linear order, then this just looks like a graph with lots of lines. If it was a partial order, maybe we get something that's a bit more tree-like. But it gives a good notion of a graph that looks a bit like the underlying structure. And then based on this, we can define the idea of a neighborhood of a structure, which is just you take a point in the graph, you take all the things that are some radius away from it, and that generates a substructure of the original structure. So for example, if we have something like this, the one radius neighborhood around A here will be, you just draw something like this, and you take all those points and they generate and you take the substructure of A generated by those, and that's the neighborhood. And so where this is going is that we have this property of first order logic called Kant's locality. And what this says is that for any property which does have a way to define it in first order logic, there will be some fixed R such that for every structure you pick, for every pair of structures you pick, A and B, if every R neighborhood of A is isomorphic to some R neighborhood of B, then both of these structures must have this property. And so this is a slightly nicer way of making the same argument that we did before with EF games. And I can show you an example of that too. So if we specialize the above property specifically for graphs, it says that connectivity of finite graphs is not first order definable if there are two graphs, G and G prime, where one is connected, one is disconnected, but every R neighborhood of G is isomorphic to one of G prime. So looking at the same thing above, all we have to do in this case is define some map from this graph to this one, such that every sort of local piece of this graph looks like a local piece of this graph. And we're allowed to make the size of the graphs vary with the value of R that we're given. So as long as we make these graphs look like big enough circles, then there'll always be some sort of a local isomorphism between them. So that's pretty cool. And it kind of maybe gives a slightly better idea of what the global structure of sort of first order definable things is. It's structures with local properties. But it would be nice if we had a more concrete classification of what are all the first order definable structures. And we can do that, but we have to take a little bit of a detour through complexity theory. And specifically, we want to look at Boolean circuits. And so these are just sort of a formal definition for like combinatorial digital circuits that are used a lot in complexity theory. And it's basically, it's a directed acyclic graph, which has some inputs or some vertices considered as inputs, a single vertex, which is an output, and then the rest of the vertices are like gates. So you have NOT gates with one input and an OR gates, which can have any number of inputs, and the output is just cloned. So I kind of think the nicest way to depict this is something that looks a bit like a string diagram, where you have all your inputs at the start, one output, and everything else just kind of as a block here. And so this defines some sort of function between binary strings of length some n and one binary output. But when we're talking about computing things, we usually want to talk about strings of arbitrary length. So actually the thing we work with is families of circuits, which are parameterized by some natural number and such that Cn always has an input length of n. And then from those, we can talk about whether a language is computable by a family of circuits, which just says, and when I say language, I'm talking about a set of binary strings. So to decide whether a specific string is decided by a circuit family, you look at its length, and so you pick the circuit that corresponds to that length out of the family. You input it in here just as the first bit goes to x1, second bit to x2, etc. And if it outputs 1, then we say that that circuit family has accepted that string. But this, as it's defined now, is a very strong notion of computability, because this map here, which goes from n to Cn, this can be any function so far, even uncomputable ones. So we kind of want to restrict that a bit, and from that we get the idea of a uniform Boolean circuit, or a uniform family of Boolean circuits. So specifically, we look at this map and we say it has to be computable on a Turing machine with in some bounded time, and usually this is d log time for purposes we're looking at. So I've written that in gray, and I'll just omit it in the future. And then from that, we can define this complexity class of languages which are accepted by uniform families of circuits and have some constant bounded depth. So I've said constant depth here, but really it's bounded, which means that the graph of the circuit should have some upper bound on the depth of it. It shouldn't go any deeper, but can go less deep. And the number of vertices should be polynomial in the input. And then we have this theorem that AC0 is exactly the class of structures definable in first order logic, except there's a slight caveat here, because in order to discuss the things definable in first order logic in a kind of complexity theoretic way, we need to be able to talk about the input in a similar way that Turing machines or circuit families do, which means we need to be able to inspect the bits of the input. That's fine, because everything we're considering is finite structures, so it is always in bijection with the natural numbers. We just have to fix some way of choosing that bijection. So what we say is we add to our logic a linear order. So actually, when we say first order logic, we're saying first order logic plus some linear order on the elements of the universe. And in that case, then yes, this is an exact equivalence between the elements of AC0 and the structures definable in first order logic. So that's pretty cool, but AC0 it's quite a boring complexity class. There's a lot of things it can't compute, and there's a lot more well-known classes. So the question is, can we classify any of them logically? The answer is yes, but we do have to strengthen the logic that we're working with. We could jump straight to second order logic, and I'll look at that in a bit, but first there's kind of an intermediate step, which is logic with a fixed point operator. How does that work? Well, first of all, we need something to take a fixed point of. And so the way this works is we introduce a fresh relation symbol, and we'll have some first order formula just defining a property of that relation symbol. And the goal is in doing this to be able to define some sort of operator which goes from, say, parset of AK to parset of AK, which we can then take the fixed point of. So we define from a structure over the signature sigma, we define a structure over the signature sigma with this extra fresh relation symbol, such that the interpretation of that relation is always some other set X. And so this is essentially adding a new symbol into the relation and then saying, okay, we can substitute it for some set in some subset of the universe. And then we obtain this we can define this construction which defines the operator as I sort of said we're looking for before, as just the set of tuples which on some input X are true for a given formula when we substitute the relation R for that input. And so it's quite a lot. I can give an example. If we turn our attention back to graphs, for example, you can define this idea of like a edge composition operator that sends, say, a set of pairs of vertices to a set of pairs of vertices. And the definition we'd like for this would be to say something like E in V squared, such that, how do you do this? There is some Y in V such that X, Y in X and Y, Z in X and X, Z in E. So what that's saying is you input some set of pairs of vertices, and then what the output of this is it's a set of pairs of vertices which are obtained by composing those as long as their composition is an edge in the graph that we're working over. And so the idea behind this is if we took the transitive closure of this, we would just get the set of vertices which are reachable from each other. And so we can define this in the way presented above as like a first order formula with some fresh symbol R, just by the formula that exists, Y such that R X Y R Y Z and E X Z. And so when you do this, then the sort of associated operator through this definition will be equal to this. And so now we want to consider adding the ability to compute fixed points of that to the logic. In case anyone doesn't know, a fixed point is just for something, some sort of ordered set like this is, and here I'm considering the order by inclusion. It's just some set, usually written mu of the operator, where applying the function to it doesn't change it, and for any other set with this property, this is a subset of the other set. So the problem here is not all operators defined in this way will have a fixed point. And so we'd like some sufficient condition in the logic to say when we can syntactically form something that should give us a fixed point. And the exact way we can do that is by saying that the relation symbol, the new one, must only appear positively. And that means that it only appears under an even number of negation operators in any formula. And in that case, the associated function on the parsets will be a monotone function, and so has a least fixed point. So in that case, we can add a new syntactic thing to the language for computing fixed points. And that gives us what we call first order plus least fixed point. And the associated theorem to this is that again with the linear order is the complexity class P, which is this class of sets decidable by a Turing machine in a polynomial amount of time. So yeah, as I said before, with that formula phi giving edge composition, if we take the least fixed point of that, then that gives us the transitive closure of the relation in this case. And that will be oh gosh, sorry, the pen's messing up. Reachability. So the idea is that this as a subset of v squared is true for two vertices if there's a path between them, and from that we can pretty easily define whether a graph's connected. I'm not going to write it out because I'm running quite low on time. And just as a fun extra point, if you, instead of a partial fixed point operator, where rather than having baked into the syntax when you can form a fixed point, it just gives you the empty set if no fixed point exists, then we get P space, which is the class of things decidable on a Turing machine that use a polynomial amount of space in the tape. So the next thing, we've classified P, we might say, can we also do NP? And the answer is yes, but we do have to jump to second order logic. And sort of like speeding through this a bit. It's second order logic, or specifically existential second order logic. It's just like first order logic, but we have variables that can range over sets rather than individual elements, and they can be sets of tuples as well as just subsets of universe. We can form predicates from them, and we can existentially quantify over them, with the caveat that the existential quantifiers have to all go at the start of the formula. Otherwise, we could just form universal quantifiers by sticking a negation in front of them. And in that case, we have something called Figen's theorem, which is the class of finite structures expressible here is NP. And we don't need the linear order anymore because you can just existentially quantify a linear order. And so a cool corollary of that is that P equals NP if and only if first order plus least fixed point plus linear order is equal to second order. And I've dropped the existential quantifier here because P is closed over complements. So in both cases, it turns out that if P equals NP, then existential second order is equal to second order. And you can argue that you can drop it in the other direction as well. Yeah, that's me.